This is my friend Nathaniel. He works on gRPC.
And today we're going to jump right into some code to start.
And we have a pretty big piece of code here. This is actually...
Hold on, where are our slides? Do we have slides?
There we go.
There we go.
So we have
right.
This is one class from a widely used, well-established piece of software. And it's pretty big. It's actually 1,700 lines, so it's kind of hard to figure out how to put it on a slide. It's got 74 public methods and 18 public attributes, plus another 45 or so private methods and attributes. And so, is this a problem?
It's big, but is this a problem? Well, it's not a problem for the interpreter. It's not a problem for the machines that run it.
And the users honestly don't care. So
it's not a problem. We're done. Quick lecture. It's a nice day outside.
Sadly, this is a problem, because software is made out of people and their time. And there's a lot of people that work on software over time, so this is a problem because it's hard to understand. The guilty party here is the local repository class from Mercurial, which we're picking on because we know it's a problem in the Mercurial community, and it's publicly visible. So you can actually go and look at this example and sort of get a feel for why it's hard in the ways we're describing.
We think local repository is lacking readability. Readability is what your code needs because you don't scale. On a successful project, you may have hundreds of collaborators working to maintain your software. There may be tens of thousands of developer users writing their own code that calls your code. You don't get to have a one-on-one interaction with all of them and answer their questions about why you made this decision, why the code functions in this particular way. Your code needs to describe itself to those people the way you would describe it.
Sadly, readability is at best a third priority when you're developing software. Software has to be correct, and it needs to be efficient. If it's not solving some problem correctly, it's kind of pointless to have the software in the first place. And if it's not efficient, you're boiling the oceans to accomplish some trivial task, so that's kind of a waste. But the good news is readability is mostly orthogonal to efficiency and correctness. So even while it's not going to be the first thing on your mind, it's still something you can always be working on, independent of how hard your software is.
Jumping into particular complaints with local repository. Our first is that we think it has a lack of cohesion. It's kind of a grab bag of a bunch of different problems, a bunch of different solutions. We think if we gave you the first half of the class to read slowly, that you wouldn't be able to guess what's in the second half.
Roughly, squinting at it from a distance, there are at least 3 different layers of components present in this one class. It's storage logic, there's business logic on top of the storage, and then it's just sort of this data container that hangs some extra stuff off to the side.
We don't like the way that it mixes function and convenience. We think it's great for a code base, for a module to include both function and convenience, but we think it's too much in a single class. We'd sort of rather see this as one class that provides useful business behavior and another class that provides a more convenient API on top of that.
This method at least has the decency to say it's a convenience wrapper and to tell you that to understand what's actually going on, go look over here. But it's still adding to the cognitive burden of understanding this class for relatively little benefit. It's 2 lines of code.
We don't like the way that it mixes layers of abstraction. Internally, it has low-level structures. It also has high-level structures that use those low-level structures. So as some maintainer in the future is reading the module, they're going to have to maintain at least 2 layers of abstraction in their head while they read the module, while they read the class.
It also just has way too many elements in its API. Most people's working memory is 7 plus or minus 2. If you can keep 10 items in working memory, that's actually doing pretty well. This is why North American phone numbers were designed to be 7 digits, because that's about how much people can remember easily. This has 92 elements, and that's if you're a client. It's over 100 if you're actually developing it and remembering everything that's going on. But that's kind of a squishy way to think of it being too many in terms of numbers. So it's easier to realize that we can't even talk about what this class does without using the language of subdivision and saying it does this and this. The fact that I had to use and in that sentence is a good clue that it could be split up into multiple types.
We think the text of it is just too long. 1,700 lines is a magazine article or a blog post. We don't think anyone should ever sit down to read a class and say, I'd better put a pot of coffee on. Now, lots of us have objected to code length in the past, but for mostly emotional or hard to describe reasons. We want to dig into that right now and talk about that. So let's look at a long function.
And this function is a little bit phony, I admit, because every line depends not only on the immediately preceding line, but all of the preceding lines that computed intermediate values. So it's this quadratic number of relationships between all the values computed in the function. And that's surprising, but fortunately not realistic. More realistic is something like this, where you use 2 or 3 values on each line, but you don't actually know that in the moment.
If we think about the process of reading this function in the moment, let's imagine we're about to read that last line, whatever line is next. It probably is only going to use the v29 and v30, the last couple values to be computed. But we don't know that until we've read it. So before we go on, we've got to maintain in our head all the available values in scope. So a long function like this is a tax on working memory, the same way that we saw before. And consider what happens when you as the reader exit the function scope. You get to throw away from your mind all those intermediate values and just retain the parameters and the return type of the method, and you get to go on to the next code element with a much more clear head. That's what's wrong with long code.
Now, local repository wasn't inflicted on the Mercurial community by some malevolent enemy who really wants to make my life difficult. It's the tragedy of the commons that comes about as a side effect of the natural software development process. And any software change has to meet these requirements. It has to actually solve a problem, and the author of the change has to understand the problem in the code base well enough to create the change. And that's fine, but then when we review the code, either by ourselves later after some delay or handing it to a colleague to get a second set of eyes, usually we're only looking at what actually changed right now, the incremental merits of the change, not the bigger picture. Occasionally we'll look at the bigger picture, but that's pretty rare. And when you couple that with the fact that we are terrible at estimating the lifespan of our code bases, we think it's going to last a few weeks and it lasts a few years, we need solutions for these problems that are really cheap, because you're only going to look at the immediate local problem, and you're only going to do that on an incremental basis. So you want some tool that works on an incremental basis that doesn't cost a lot now, because if I give you a solution that costs a ton of time and will keep you happy in 10 years, you're not going to do it because you think your code's going to last 6 months, and then in 2 years, you're already in a world of pain, and it's too late for these to help ahead of time and avoid the pain.
So we're going to develop some silver bullets, and we're going to start off with a pretty famous quotation. How many of you have seen this before? Everybody's read The Mythical Man Month? Okay, many of you. We usually come across this quotation when we're talking about the relative value of learning a system by examining its behaviors versus examining its data structures. And we agree with the claim here, but that's not why we bring it up. We bring it up because he's saying he can understand your code without understanding your problem domain, just by reading your code. That's a quality that we're going to retain in the silver bullets that we present here today. And that's good because learning a new problem domain cannot be made generically easier. But fortunately, most of the problems that come with readability, and most of what comes out of good readability in code, comes from code structure, not problem domain. In particular, we think that the two big challenges of readability, the two big objectives of readability, are understanding how state is maintained and changed throughout your code, and understanding how program control is passed from one system to the next. So if those are apparent, the code is usually very readable. If those are obscured, like, say, by out parameters.
Yeah, out parameters are maybe a little unfamiliar to people that write mostly Python, but they're common in languages like C++, where you can only return one value. So if you need to return an error and some useful data, you're going to have this out parameter. So there's state change intentionally happening on the wrong side of the equal sign, and it starts to obfuscate the code flow, especially if you're not used to that. Similarly, mutable global state serves as this magical hidden input to the entire system, and when it changes, things can happen that surprise you later.
So a magical hidden input in the physical world would be like some sort of background interference. Why do we perform experiments in laboratories in the physical world? Because we want to screen out background interference. Similarly, if we're working with a delicate mechanical creation process, manufacturing process, we'll do that in a clean room to screen out contaminants. And the principle from the physical world here is to do where the doing is simplest, possibly in some artificially simplified environment that had some cost associated with construction with it, but to screen out background interference, to screen out contamination. We can take that into software by saying, code where the coding is simplest. That seems pretty great. Let's try to apply it. Let's imagine that we are maintaining this piece of code.
And this is the shortest class we're going to have on our slides. It's really simple, at least at first glance, but there's a bunch of questions that you have to ask about this. Like, is answer actually something that's being overridden from the base class? And so this is actually a subclass of foo that behaves wildly differently because of this one line of code. Is this being used from outside the class? It's public, so somebody else could be using it. It could be shadowed, it could be overridden. The point here is that placing code at class scope, any kind of code element, invites a lot of questions that your maintainers then have to answer before they can do any changes to that code base.
The simplest way to answer your future's maintainers' questions is to prevent them from even being asked. So avoid placing elements at class scope unless you have no alternative. And a reason for which you might have no alternative, well, we've seen reasons like, it looks nice. I really want it there. Or our favorite is the code element is only ever used from the class. And we love getting this one because it has just such an easy response to it.
So if the right place to put a piece of code that's only used once is nested inside the place where it's used, and you take that to its logical conclusion, you should just write everything inside your main function. We don't need modules or anything. Just one smash it all in there.
50,000 line main function, because everything's only ever used from within the main function, so it should be syntactically nested inside.
And what we mean by only putting something at class scope, if it has to be there, is the class is broken if you don't put the code element inside the class. If it could possibly live outside the class, you're probably better off with it living outside the class to avoid causing all of those questions.
So where is outside the class?
It's in the module. This is Python. We don't have to put everything inside classes. This isn't Java.
You should put everything at module scope. You should only promote code elements to class scope when you need to. So classes, go at module scope. Functions, great at module scope. Constants, module scope. A single test input string and a single test method.
Put it inside the test. It's probably better to have it nearby anyway.
It's probably fine.
You don't have to be super rigid about this. Now, we've spent a lot of time talking about what classes complicate. So let's talk about when it's useful to actually use a class. We're not saying never use classes. You just need to be realistic about what they're actually for.
And only use them for what they're for.
The first thing we think classes are good for is structuring and aggregating data. In C, this is just a struct which can't even carry any behavior along for the ride. In Python, it looks like a name tuple or some sort of data container like a protocol buffer. There's no real behavior there. It's just some data that's coming around and being passed around as a logical structured unit to make it easier to work with.
The second use of a class is to define a type. So if I'm implementing some system and I need some behavior to be provided by its users, I'll define a type. And I'll say to the users, you need to implement this type in order to pass it to my system for the system to fully function.
And going along with that, you can implement types that have been defined with classes. That follows on fairly naturally. And then the last thing that classes are useful for is to create a bunch of instances that are basically the same, but behave a little differently, mostly according to when they were constructed, or how they were constructed. And this is a really fancy way of talking about the thing you always used classes for, right? You have a square, and the square can have different length sides or be different colors, but they're all the same type.
Now, legitimate classes, we think classes are healthy when they don't mix these roles, except for the last two. It's very common to mix the last two, to implement a type and provide arbitrarily many instances of that type.
The interface might be the square knows how to draw itself to the screen, and the implementation that is variadic is how the square is shaped in terms of size.
But some things that classes are not for are being functions. And you might think, how how can this be? They're so different. Syntactically, operationally, dynamically. Well, we see a lot of code that looks like these first two lines, where there's a class, and the only way in which the class is ever used is to instantiate and then call a single method, and then the instance is thrown away. We call this a class that wants to be a function, and we can transform it into a function by eliminating the local field and chaining the constructor and the method call together, and then renaming the method from whatever name it had to just call, since there was only ever one public method on the class.
And now it's really obvious what's actually happening. You actually have a function with two arguments, and if you just make it a function, a whole bunch of questions about what happens between construction and calling that method just go away because it's now a bunch simpler.
More spurious classes that we see are classes that are namespaces. Maybe they're instantiated, but nothing is never done with the instance, like it's never returned from a method, it's never stored in a list, or maybe they're never even instantiated at all. Python has namespaces. They're called modules. Use modules for namespaces. Classes are more complicated. We also see spurious classes being used for what we'll call enumerated polymorphism. This is kind of like polymorphism, where you want to define a type, but instead of there being potentially infinitely many instances and implementations of that type, you have in mind the 2 or 3 or 4 implementations that you think will be all that ever need to exist.
And so you write some base class like this, which is basically what we just talked about, a class as a namespace. This class doesn't really have a reason to justify its existence as a class, but then you have a set list of subclasses that you make that share no behavior. You're really just using the base class as a stand-in for an abstract base class as well as one of the behaviors.
Don't abuse class objects this way. The language has the ABC module for polymorphism. Your future maintainers expect polymorphism to use the ABC module. Go with that. Now, how many of you have seen the movie where an alien object crashes to Earth and a scientist finds it and takes it to the lab and starts to work with it and tries to use it for good, but it starts taking over and the scientist becomes the villain and has to be defeated, and at the end of the movie the scientist says, "I tried to merely use it, but I became it."
So this
Okay, good. We've all seen that movie. These are Mixins. Mixins try to be helpful. Mixins, they want to help, but the mechanism by which they are used is inheritance. So your class cannot use them without also becoming them, without adding them to the type that it exports as part of its API, and likely without also adding all of the Mixins public methods as well. We think your class doesn't want that kind of help. We've seen how that movie ends.
So we've spent a lot of time talking about what classes are for. And so now in the unlikely event you still have a class in your code, not actually that unlikely, it's worth spending some time talking about things you can do while you're designing and implementing your classes to make them less confusing to maintain. And the first one, and probably the most important, is to avoid self-use of public APIs. This isn't always bad in terms of causing real computation problems, but it often confuses things. It typically betrays some layering violations where there's 2 layers of the object that could be disentangled. It's also, if you're wanting to use inheritance for some reason, a great way to make your class hard or impossible to subclass. We're not going to cover that in detail. It's covered really well in effective Java. It's item 17, and that's worth reading and meditating on.
We think that you should avoid passing the self-reference out of your class. We think that from within your class, you should only call down in layers of abstraction. But if you pass your self-reference out of your class, then the system to which you've passed your self-reference could call any part of your public API on the object that you just passed. So it calls into question whether the other system is at a lower level of abstraction or a higher level of abstraction. The way out of that situation is to ask yourself, do you really want the system to which you passed your self-reference to be able to call any part of your public API? Almost always the answer is no, and points to what you really want instead, which is to pass the value of an instance field or several instance fields wrapped up in a helper type or a bound method or something smaller than your object's entire self.
You should also minimize the amount of state you're keeping track of on your instances while performing computation. State's great when it comes in at construction time. It's really confusing if it's temporary during the process of handling a single function call. Because what you end up with is, oh, this method calls these 6 other methods, and some of these inputs need to go to some methods, and I don't want to pass them around. You squirrel it away on self, and then when you're done, you forget to clear it, or the call happens from multiple threads, and suddenly your object is no longer thread safe, and it's just a mess.
Early in my career, I tracked down a huge memory leak with exactly these circumstances, where memory or method-specific data was passed to an instance method on a long-lived object. And the author of the class didn't want to pass all those parameters down several layers of instance called, so they memoized it in a field on the instance, and then they forgot to clear it at the end. So that instance, which was long-lived, retained a large amount of memory which was intended to be short-lived.
So we spent a long time talking about classes, because classes invite all of these questions and have all of these special, unique to classes pitfalls. But we have a few things to say about modules.
Always place your imports at the top of your modules. You may have mutual recursion among classes or functions, but we think that in healthy code, you don't have mutual recursion among your modules. You have a directed acyclic graph of modules. By placing your imports at the top of your modules, you can maintain that. You can enforce that programmatically.
It's also good to import the modules you're referencing in your specification. And this is a little curious, because Pylint would actually complain about this code because the reference module looks unused. But really what's happening here is the module that you're actually using, where you're calling this create useful variable or useful value function, returns some type. So there's an implicit dependency between these modules. And if you had some sort of type analysis like MyPy running over this code and you had annotated all the types, it would become explicit because you need to tell the type checker, I'm returning something of this type and it would need to be locally available.
We think that you should default to putting all your code elements at private visibility. Only promote things to public visibility after you've made an intentional decision to include them in your module's public API. We've looked into why this happens. To a lot of people, it just doesn't occur to put the underscore in place, or the underscore looks unattractive. So train yourself to put an underscore in front of every name you define and only remove it when you've decided that you really want to. It only looks weird the first 800 times.
I actually recently tripped over this upgrading a library where something had been intended to be private and was unintentionally public, and something broke when I went to do the upgrade. It was quite surprising. So those are all sort of the easy things that you can internalize and trust yourself to follow. But there are times in life when your judgment is compromised. It's like Odysseus and the sirens, where he knows the sirens are going to sing this beautiful song, and then the crew will sail to their island and they'll all die. But he wants to hear the beautiful song, so he has himself strapped to the mast because he knows his judgment's going to be compromised. And in software, your judgment is also occasionally compromised.
So let's imagine the case where you've had a problem for a week, and you've been understanding it and designing your solution and coding your solution and testing and debugging, and you've been thinking about the problem while you've been working on it, but also over meals and last thing before bed and first thing in the morning. You've got the problem on the brain, you've cracked it, you've solved it, you've delivered useful behavior for your users, and that's great, but are you really the best person in that moment to decide what's obvious about the problem and what's obscure and what needs to be commented versus what's self-evident? We think that you probably aren't. Perhaps you do too. And what if you had signed up earlier for some restriction on yourself, knowing that your judgment would be compromised later?
This is where things like enforced line limits and complexity limits really help, because the longer you've spent understanding a subject and authoring the code that solves the problem, the more obvious the whole thing is, until you've got this 1,000-line or 200-line long function, and anytime somebody asks you to split it up, you respond in some way like this, where, oh, if you actually understood the problem, I promise there's no way it could be made any simpler.
How many of you have heard a response like this when you've asked someone why their code is too long?
And how many of those times could you actually find a way to split it up later? Yeah, most of the time. And you don't want to investigate a bug in a 1,000-line class or a 200-line function, but it still feels hard in the moment to figure out how to conform to these line limits. And really, what it is sort of unintentional intellectual laziness. You have this long function. Again, it's phony because the scroll was funny once. You have this A, B, C that are inputs, and an X, Y, Z that come out. And that's it. That's really what the function's about in terms of what I care about when I'm writing it. But that means it's huge and kind of a mess.
So the function may be about A, B, and C, and X, Y, and Z at its public API, but chances are that if its body is huge, it's actually about D through W in the middle. So go ahead and define those D through W with your future maintainers in mind. You don't have to include them in your public API. In fact, it's highly likely that you won't. But they will tell your code's future maintainers where the rest points are, where the intermediate values are, where the checkpoints are.
And setting up private data structures so that things move around in more understandable and predictable ways will really help even you when you come back to that code in a year and are suddenly cursing the moron that wrote it only to discover that your version control system is telling you that it was you.
You may think when you're defining intermediate classes, partial results classes, that some of them are too obvious. Well, better too obvious than not obvious enough. We are coding unto others today.
And these intermediate concepts feel like they're adding complexity, but it's only in the moment when you think everything is obvious that adding these concepts really seems like it's more complicated. They're abstractions that help you understand things better later. That's the point.
Don't abbreviate when naming. This is not to say don't use abbreviations when naming, but don't create new abbreviations when naming. You get to use existing abbreviations like HTTP and TCP, but software engineering is getting more and more cosmopolitan by the day. The person who maintains your code in the future may not speak your native language or the native language with which you're coding at the time that you're coding. Give that person some extra help.
Or they
Spell
might
out
speak
your
a different
names.
subset of that language. And
Right.
there are times when you're going to use abbreviations from your problem space field. Like if you're writing biology-related code, you're probably going to have a bunch of classes that talk about DNA, and you don't need to write that out, because that's a common abbreviation you can understand anybody with basic exposure to your problem to know. But if you write out these horizontally wider names, dictionaries are actually useful tools for people.
In storytelling, there's the normal course of events is that characters are introduced in isolation before they are observed or described as interacting with other characters or interacting with the environment. So if you go to see a play or a live performance, you may see a cast of characters like this. If you watch a sitcom, you may see a title sequence with a theme song that explains how everybody got where they are. This is done so widely that when it's not done, it's actually a narrative technique to jar the reader, to surprise the reader when a character suddenly appears.
Or to scare the reader. And we don't like being surprised or scared when we're reading our source code. That's generally a bad thing.
Let's walk through reading this block of code here. We see a new function that defined. That's great. We get to learn it. We get familiar with it. Then we see another new function defined. That's great. And we get to learn it and remember it. Then we see a third function defined that calls the first function, and that's OK. And it calls the second function, and that's OK. And then it calls something we haven't yet learned. And we have to pause our comprehension, we have to pause our understanding, and look ahead to find out about what that is. And it's surprising, it's jarring.
And when this happens, this is the point when you print out source code, or you have like 6 editor windows all open with the same thing, because you're trying to figure out what's going on and what's coming from where, and you have to keep re-entering this one function you're trying to understand. But the solution is really easy. If you sort your code elements so everything is defined and introduced before it's used, this goes away. And only mutual recursion gets in the way of sorting your functions this way. But that's not something you do every day when you're writing code. It's a sometimes food of programming.
Now, this will have the effect that in your modules, your private implementation will float to the top, and the public elements of your modules will descend to the bottom, because your public elements call your private elements and not the other way around. We get some pushback about this when we give this advice. And most of the pushback we get is, but I want my public parts of my module at the top so that the users of my code don't have to scroll.
And that's That's an interesting frustration because the maintainers of your code and the users of your code are two very different audiences of readers. The maintainers have to be in the code. It's necessary for them to read and understand the code to do their job. The users probably don't actually want to read your internal source code. They're not interested in that. You can please all of the people some of the time, and this is not one of those times. What you should be doing is providing generated or handcrafted documentation for your users so they can see the public parts of your API that they actually care about. And now maintainers who actually are required to read your files get things in an order that makes sense for them.
So go forth today and code unto others. Remember that the readability of your code is independent of correctness and efficiency in problem domain. Remember that classes invite questions and invite complexity, should be used minimally and sparingly and only for legitimate purposes. Consider setting your own judgment aside and obeying some codebase-wide rules that ensure kindness to everyone. And when you're forced to choose between writing your code with future maintainers in mind or writing your code with its users in mind, favor your future maintainers. Thank you very much for coming, and we'll take your questions.
Thank you. So if you have questions, you can come to the microphones, and we can take a few questions now. All right. Thank you very much.
Thank you.
Thank you.